This is number 8, and this is 25, 2. I have a huge plate with an area A, and there is a charge plus Q on the plate, and I have at a separation little d, same area A, and I have minus Q charge on this one. Well, the electric field outside these huge plates is going to be 0. And I want you to prove that using Gauss's law. E is 0 here and E is 0 there. And it's not because I am lazy, but I also want you to prove that the electric field inside is constant. I already anticipated that earlier. And that the electric field inside E equals the surface charge density sigma divided by epsilon 0. And the surface charge density sigma is defined as Q on one of the plates divided by the area of one of the plates. So it is Q divided by A divided by epsilon 0. That is the electric field. And if the plates are very large compared to D, it is constant throughout. There are some fringe fields here, we will ignore them. And to a very good approximation will the E field outside the plates be 0. The potential difference between the plates, delta V, is the integral E dot dl. Well, when you go from here to here, E and dl will be in the same directions, so you get a plus sign there for the cosine of the angle theta. The integral of dl is simply the separation d, so you get that the potential difference is that value E that you already calculated here times d. And so that becomes Q divided by A epsilon 0 times d. We define the capacitance of two metal surfaces, spheres in spheres or cylinders in cylinders or planes parallel, whatever. We define capacitance as the charge on one of them, assuming that the charge on the other one is the same, divided by the potential difference between the two. It is the ability to carry a certain amount of charge for a given potential difference. If this number is large, it can carry a lot of charge for the same potential difference. And after what we have just done, you should be able to show very easily that for a plane capacitor, the capacitance is A times epsilon 0 divided by D. And the unit is in farads, in SI units. It's linearly proportional to the area. The larger the area, the more charge it can contain. That is intuitive. It's not so intuitive that it's inversely proportional to D.